This is Chemistry, Chapter 11, Section 2. And in this section of our book, we're looking at actually 4 different laws, but only one of those is really important. If you've done your reading, you saw that we have Boyle's Law, Charles' Law, and Gay-Lussac's Law. All 3 of those laws are placed together and combined together in the combined gas law. And this is the one that we are going to be concerned with, because this one will actually become any of those other 3 depending on what you're holding constant. And we don't really care whether we're using Boyle's Law or Charles' Law to solve a problem. We just want to get the correct answer. Okay, so there's one thing that you need to remember here, and that is PV over T. That is your combined gas law. If you can remember that, you can write out the combined gas law anytime you want it. Our combined gas law actually looks like this. P1 V1 over T1 equals P2 V2 over T2. All right, and the subscripts 1 represent an initial set of conditions. The subscript 2's represent a final set of conditions. So you have on the left-hand side there your initial pressure, initial volume, and initial temperature. And on the right-hand side, your final pressure, final volume, and final temperature. Okay, so this is the combined gas law, and that's the one that we will use to solve the problems. Now, I'll show you on a sample problem here how we go about doing this. What I like to do is, first of all, just write P1, V1, T1, P2, V2, and T2 down the right-hand or the left-hand side of my paper like this. And then as I read through here, I'm going to put the numbers in where they belong. Okay, so first reading the problem, a sample of oxygen gas has a volume of 150 milliliters when its pressure is 0.947 atmospheres. What will the volume be at a pressure of 9.87 atmospheres? Okay, so let's go through here and pull out the numbers. A sample of oxygen gas has a volume of 150.0 milliliters. That's our initial volume. So we have 150.0 milliliters there. When its pressure is 0.947. So that's our P1 atmospheres. Okay. Then we're asked, what will the volume be? We're being asked to find the final volume at a pressure of 0.987 atmospheres. Now you'll notice that nothing is said here about the temperature, and so that remains constant. So if we start out with our combined gas law, P1 V1 over T1 equals P2 V2 over T2. Since we don't have values for T1 and T2, we assume that it's held constant. In some problems you'll be told that that quantity is held constant. But we can just cross those out. So our equation becomes P1 V1 equals P2 V2. Now if you're really interested in it, that's Boyle's Law. Boyle's Law involves a relationship between pressure and volume. But to be perfectly honest, we don't care whose law it is. We just care that it's going to work for us. All right. So now I'm going to solve this for V2. And I get V2 equals P1 V1 over P2. Now we can just go ahead and put the quantities in there then. P1 is 0.947 atmospheres, and V1 is 150.0 milliliters over P2, 0.987 atmospheres. If you look at that, atmospheres will cancel out and we'll get our units in terms of milliliters, which is what we'd expect for the volume. And when we do the arithmetic using the calculator, we end up with three significant figures, 144 milliliters. There's your answer. Okay, so you see we didn't really care whether we were using Boyle's law or Charles' law or Gay-Lussac's law. We just, by using our combined gas law, it became Boyle's law, but like I say, who cares? We got the answer that we were looking for. We were able to solve for V2. Now, this sample did not include temperature, because there is one very important consideration when we're dealing with temperatures, and that is this: temperatures must, I cannot emphasize that enough, must be converted to kelvins. Okay, we have to put our temperature on the Kelvin scale. We are not allowed to use temperatures in Celsius degrees when we're solving these problems, and that's fairly simple to do. The Kelvin temperature, this is the equation that you use for this, is equal to the Celsius temperature plus 273.15. Okay, so if you're given a Celsius temperature, you need to add 273.15 to it to get the Kelvin temperature. Now, because of the way we do addition and subtraction with sig figs, if your temperature does not include a decimal portion, for example, if you're just given a temperature of 20 degrees Celsius, or let's say 22 degrees Celsius, you can ignore the 0.15 here, because that's just going to round off when you do this conversion. So you only need the 0.15 if you have a decimal part of the temperature. So we'll take a look at a problem that involves that. Alright, so let's take a look at this problem. It says a gas has a volume of 1.75 liters at minus 23 degrees Celsius and 150 kilopascals. At what temperature would the gas occupy 1.30 liters at 210 kilopascals? Alright, well, let's first of all list all of our quantities down the side of the page here, and I'll make a little more room here for myself. There we are. Okay, so we have P1, V1, T1, P2, V2, and T2. Okay, so a gas has a volume of 1.75 liters. That's the initial volume. At minus 23 degrees Celsius and 150.0 kilopascals. That's the pressure. Okay, those are our initial conditions. It says at what temperature, so it's asking us to find T2, would the gas occupy 1.30 liters at 210 kilopascals. Alright, now the first thing we need to do here is to first of all convert our temperatures. Remember, we said that temperatures have to be converted to kelvins, and so I'm going to take my minus 23 degrees Celsius and I'm going to add to that 273. Now, I mentioned before that when you do not have a decimal portion, as this one does not, there's no decimal portion to that temperature there. And so I can ignore the 0.15. You recall we said 273.15. However, if there's no decimal portion, that's just going to round off anyway when we do our rounding. Actually, let me show you that one. If we take minus 23 and we add 273.15, all right, when you do that addition, you're actually going to subtract 23 from 273, and you get 250.15. However, remember our rules for sig figs for addition and subtraction are you round to the column of the leftmost last significant figure. Here's the last significant figure in that digit. In that number, it's a 3. Our last significant digit here is the 5. Which one is furthest to the left? It's this one right here. So we're going to round to that decimal place. So we can write this as 250 point kelvins. Okay, that's how we do the addition subtraction. I won't go through all that detail every time I do that, but it's worth seeing right there. Okay, now let's start with our equation. Remember, we have P1 V1 over T1 equals P2 V2 over T2. All right. First of all, we're going to solve this for T2, and so it's actually easier to flip. This is a proportion. You might remember that from math. One fraction is equal to another fraction, and we can turn it any way we want to. So I'm just going to flip everything over. So I'm going to write this as T1 over P1 V1 equals T2 over P2 V2. All right, and now to solve for T2, I'm just going to multiply both sides by P2 V2, and I get the equation that I'm going to use. T2 equals T1 P2 V2 over P1 V1. All right, now let me also say that some of you may want to solve algebraically like this. I prefer that method. But there's no reason why you have to. Some people like to just plug in the numbers and go. And you can do that. Just be careful of the significant figures when you do that. If you start solving things and rounding, you don't want to use rounded numbers in your calculation. So if you're going to, for example, in this one, if you're going to solve for P1 times V1, you got to keep all the digits that you get when you do that multiplication, because you're not done until you use that to divide T1 times P2 times V2 by that quantity. So don't round if you're going to do that, but you can do that. Just plug in the numbers into the formula and solve it if you prefer that. As I said, I prefer doing it this way because now I can just put my numbers in here. I'm going to move things over a little bit. These problems usually get kind of long. Okay, so we have T1, which is 250 point kelvins, times P2, 210.0 kilopascals, times V2, which is 1.75 liters. All right, and then, that's not right. This is V2, which is 1.30 liters. Okay, over P1 V1, P1 is 150.0 kilopascals, and V1 is 1.75 liters. Now, one thing that's good idea to check is to make sure that, for example, your pressures are in the same units, in this case both kilopascals, and that your volumes are both in the same units. All right. Now, that being the case, I can cancel out kilopascals, liters will cancel out, and I'm going to get my answer in kelvins, which is what I would expect. Okay. All right. When I do the arithmetic, I come out with my answer of 260. Well, that worked out nicely. Point, because that's 3 sig figs. If you look here, we've got 3, 4, and 3, 4, and 3. It's all multiplication and division, so we'll have the same number of significant figures as the factor with the least. That would be 3. And our units on this then is the kelvins, 260 kelvins. All right. If we want to, then we can convert that. And now you were not told specifically to do that in this case, so you wouldn't necessarily have to. But usually you want to give the temperature in the same units that the original temperature was given. 260 kelvins. To convert this back, you simply subtract 273 from this, and you get minus 13 kelvins. And again, that's the correct number of significant figures. Okay? So, I'm sorry, not kelvins. You get minus 13 degrees Celsius. Okay? And that's how you do these problems. That's basically all there is to these problems. Remember, temperatures have to be converted to kelvins before you plug them into the problems. Other than that, make sure that your units are all consistent, that your units for pressure are the same, your initial and final units for temperature and volume are all the same. And then you'll do fine on these.